Hello, sixth graders. This is the first instructional video for our 2020 to 2021 regular school year. We've had a lot of fun and learned a lot with our summer instruction, but this one here is intended for the school year. I will assign you as a homework assignment to watch this sometime early in the school year. And I've decided to begin these regular school year instructional videos with algebra. A word about algebra. It's a word that comes from Arabic. There was a time when Arabs, Muslim Arabs, I believe, were at the peak of civilization around about the year 1000 around the Mediterranean Sea in northern Africa, what we call the Middle East, and parts of Europe, like Spain in particular. The Arabs were very learned in math and science, as well as other topics, and they studied some of the ancient mathematics, developed it further, and then as different cultures arose and became more dominant in Europe, after about 1000 AD, those cultures benefited from the work that the Arabs had done in mathematics, sort of a bridge between the ancient world, the ancient Greeks and Romans, and into the modern world. The word algebra comes from Arabic, and it means something like putting the pieces together or solving a puzzle. And it's spelled like this. Algebra. Well, what is algebra? It means different things in different contexts. With a small a here, it means taking an equation with an unknown quantity and figuring out what that unknown quantity is. With a small a, algebra can be done by first graders or even kindergartners. Let me explain the difference. Here's an arithmetic question. 2 plus 3 equals what? Or what is 2 plus 3? That is not algebra. That's arithmetic. And the answer, of course, is 5. But if you ask instead, what plus 2 equals 5, what plus 2 equals 5? Now, it's quite obviously 3, but that's algebra because you're determining what a missing number is to make a true statement. It's a little bit different than the arithmetic question. Now, if we write algebra with a capital A and then maybe put the number 1 after it, or the number 2, algebra 1, algebra 2, now we're talking about traditional math courses that are taught in high school. Here at St. John's, we teach most of our 8th graders Algebra 1, the high school Algebra 1 course. Some students out there in the United States take Algebra 1 as 8th graders, some take it as 9th graders. That is a collection of material, most of which is beyond you right now as new 6th graders. The high school Algebra 1 or Algebra 2 is certainly beyond you, but that's not what we're talking about. We're talking about small a algebra, which even a first grader could do, as I just indicated. I've written on the board a very non-controversial statement that I think you can all agree to. 12 equals 12. And I've also made a very crude diagram of two people on a seesaw. And that seesaw is in balance. It's perfectly parallel to the ground. So presumably I guess the two people on the seesaw have the same weight. Well, if we were to put a 10-pound weight in the hands of this person and a 10-pound weight in the hands of this person, once we've done both of those, the seesaw would stay in balance. Or if they've already got those 10-pound weights and we take the 10-pound weight away from each side, then the seesaw stays in balance. So this leads us to the approach that we take to solving algebra equations, the theory that we use. And it's really one of those statements in math, one of those assumptions that is pretty obvious and difficult to argue with, that if we have a true statement like 12 equals 12 and we do the same thing to each side, the statement will remain true, just like if we were to add the 10-pound weight to either side of the seesaw. So if I add 5 to each side of 12 equals 12, plus 5 plus 5, of course, I still have a true statement. 17 equals 17. If I were to subtract 5 from each side, minus 5, then we have a new true statement of 7 equals 7. And by the way, we sometimes say that an equation is in balance. It's balanced. When we receive the algebra equation, it is balanced. How do we know that? The equal sign. The equal sign tells us that it's in balance, like the seesaw. We could multiply each side by the same number. Times 4, and get 48 equals 48, a new true statement. And finally, we can divide each side by the same number, as long as it's not 0. You can never divide by 0, but we can divide each side here, let's say, by 4. Divide each side by 4, get a new true statement of 3 equals 3. And notice that I use the preferred way of indicating division for middle school. More and more as we go on, we will indicate a division with a fraction bar. This says two things at the same time. It says 12 fourths. It also says 12 divided by 4. So let's look at our first algebra equation. We are actually going to do 8 of them. The reason we're going to do 8 is there are 4 operations, and we're going to do 2 of each. You'll see what I mean in a moment. I think this is the algebra equation I referred to earlier that a first grader could do. You could put this into words the following way. What plus 2 equals 5? The x here is a number. It is a number, but at this point it's unknown. Well, we know it's 3, but pretend that we don't know what it is. To solve an algebra equation, we make an assumption. The assumption is there is a number. We can put where the x is to make a true statement, and then we have to go about finding that number. Okay? If a first grader received this algebra equation, it would probably be a box instead of an x. And the first grader would write a 3 in the box. What we're going to do eventually is say x equals 3. And that's going to be what we call the solution. The solution is the number that we can put where the x is to get a true statement. We first assume that there is such a number, then we find it, and then we prove that it is the solution. So how do we go about doing that? We can do the same thing to each side. Earlier, when I had 12 equals 12 and I did the same thing to each side, I kind of chose numbers at random. But when you're solving an equation, you have to be strategic. So here's what I'm going to do. Minus 2 and minus 2. The first thing I want you to notice is I did the same thing to each side. I subtracted 2 from the left and I subtracted 2 from the right. This is a good time to talk about left and right. Anytime you receive an algebra equation, it is divided into a left side and a right side. And the thing that divides it into the left side and the right side is the equal sign. The equal sign is what tells us that it's in balance, and it is what creates the left and the right sides that we have to do the same thing to. Now, I chose to subtract 2 from each side. Why? Well, look at that left side. X plus 2 minus 2. There's actually something, I believe, in the very first lesson of the 6th grade textbook called the associative property of addition. And this minus 2 here could be seen also as adding negative 2. I think we looked at that at the end of 5th grade or over the summer. So just a little reminder that we subtracted 2 from each side, but equivalent to that is adding negative 2. Adding -2 is exactly the same thing as subtracting 2. So here, when we write it this way, we have x plus 2 plus -2. We have three numbers being added together. The associative property of addition tells us that we can add those two first. We don't have to go left to right if everything is addition. And it is if we think of it this way. We can do 2 plus -2 first. And what is that? 0, right? 2 plus -2 is 0. Or if you want to see it as 2 minus 2, also 0. So now we have x plus 0. Because the 2 and the -2 added to 0. How did that happen? I made it happen. You have to be strategic about solving an algebra equation, keeping in mind what your goal is. Your goal is to get the x by itself equal on one side and then equal to a number on the other side. And when you see the plus 2 here, you have to think, hey, if I subtract 2 from that, it's going to be 0. Or if I add -2 to that, it'll be 0. Then I'll have x plus 0, which is the same as x. You don't have to write the x plus 0. I don't recommend that you do. You could just come directly from bring this x down here. And of course, the right side, we had to do the same thing to each side. And 5 minus 2 or 5 plus -2 is, of course, 3. And there you go. We're done. We know that 3 is the solution. It's obvious. But in the future, it won't always be obvious that what we have is actually the solution. So in theory, whenever we solve an algebra equation, we should prove that what we got for the x is, in fact, the number that makes a true statement. We should take that solution and put it where the x is and make sure we get a true statement. The original equation was x plus 2 equals 5. If we put a 3 where that x was, we get 3 plus 2 equals 5, which is of course a true statement. You can say, if you want, that we've just checked it. We've checked and we have proven that 3 is the solution. I know this sounds very simple, but when the numbers get more difficult to work with, like fractions, or when the algebra equations get more complex, everything in this video is going to be just one step. There are 2-step equations, 3-step equations. And if you just, pay attention closely all the time, do what's asked of you, do a little of the work, and correct any mistakes you might make, you will get to the point where you can solve the more complex equations soon enough. Algebraically, this equation is exactly like the one before. We're going to solve it the same way that we solved the one before it, except the numbers are a little more challenging. You won't know immediately what the x is, although I bet a lot of you in a few seconds mentally can figure out what the x has to be in order to have a true statement. But what are we going to do to each side? Well, we have x plus 3/5. If we can add something here that will add with the 3/5 to get 0, then we will have isolated the x. Our goal is to get the x by itself, and then whatever we get x equals a number, that number is what we call the solution to the equation. It is what we can put where the x is to get a true statement. How about if we subtract 3/5 from each side, or add -3/5? Minus 3/5 minus 3/5. I've just done the same thing to each side, so the equation stays balanced. Remember, the sides are determined by the equal sign. We have the left side and the right side around the equal sign. 3/5 minus 3/5 is 0. So the left side is simply x. These two add to 0. Technically, we get x plus 0, but x plus 0 is x, and you don't have to write the x plus 0. But if we subtract 3/5 from the left, we have to subtract 3/5 from the right. Now, when I first taught you to add and subtract fractions, I taught you that you can get the common denominator by multiplying the two denominators. You could use a common denominator of 50 here, but there's a much quicker way, and that is to simply use tenths as the common denominator and convert the 3/5 to 6/10, right? Isn't 3/5 the same as 6/10? Multiply the top and bottom by 2, right? So now we have 9/10 minus 6/10, which is 3/10. Right? 3/10. That's our hypothesis, our theory. Our theory is that if we put a 3/10 where the x is, we will get a true statement. Now, for practical purposes, you're not always going to check your solutions like this. But in theory, you should. Right? Depends how much time you have, whether I ask you to, how confident you are, and so on. But if we take that 3/10 and put it where the x is, you see these red arrows here? I've taken the 3/10, which is the solution. And really, we're kind of done. That's our answer. You might want to call it the answer. The word solution is usually reserved for this algebra situation. You know, like 2 plus 3, the answer is 5. We don't usually use the word solution there. But we use the word solution when it's an algebra equation. So we're done, but technically we should always prove that 3/10 is that number that will make a true statement. So we have 3/10 plus 3/5, and we want to know, does that equal 9/10? The original equation was x plus 3/5 equals 9/10. I put a 3/10 where the x is. And of course, this 3/5, just like when we did over there, that 3/5 is 6/10. So we have 3/10 plus 6/10, and that certainly is 9/10. So we have done two equations, solved two equations. The second one a little harder than the first because of the fractions, but we solved them the same way. There was an addition in the equation. It was x plus a number. So we wanted to subtract that number to get 0 here and do it to both sides, each side. That's how we solve those two equations. Here's our third equation. X minus 2 equals 5. Now here's a common mistake for people that are first learning to solve algebra equations. Students see a 2, a 5, and a minus sign. Well, it's a normal and natural thing when students around your age see a 2, a 5, and a minus sign. You look at this and say, oh, 3. Right? But you're not being asked what is 5 minus 2. If you were being asked what is 5 minus 2, then the answer would be 3. But what you're being asked here is what minus 2 equals 5. That makes it an algebra equation. Let me make this point. I've suggested that 3 might be an answer that some people would come up with that's wrong. What if you put a 3 where the x is? What do you get? 3 minus 2 equals 5. That's not a true statement. 3 minus 2 is 1, not 5. The solution to an algebra equation is the number that you can put where the x is to get a true statement. We assume that there is a number we can put here to get a true statement, then we go about finding it. What do you think we're going to do to each side of this equation? With the goal being to get the x by itself. We want to get x equals. We want to isolate the x. This time we're going to add 2 to each side. Why? And as soon as I write a plus 2 here on the left, I have to write a plus 2 on the right. You have to do the same thing to each side of the equation. Same thing. Why did I add 2? Because I wanted these two numbers here to add to 0 so I would get x by itself, right? And again, you're not going to write the x plus 0, but technically that's what happens. We had an x and then we had minus 2, adding negative 2 to the x or subtracting 2. Well, if we add 2, then that negative 2 and that 2 add to 0 and we get the x by itself, which we want. And we have to add 2 to the right side to get 5 plus 2 or 7. So the solution to this equation is not 3, it's 7. Because 7 minus 2 is equal to 5. I mean, as I've said, we technically should check it each time or prove that 7 is the solution. And if we put the 7 where the x is, I'm not going to rewrite it, but we get 7 minus 2 equals 5, a true statement, so we're done. Now notice, in the first two equations, when we had x plus a number, we subtracted from each side, right? Now we have x minus a number, so we're going to add. In both cases, we're getting those two second numbers to add to 0 and go away, leaving the x, okay? Addition and subtraction reverse each other or undo each other. That is often said, and that might help you to understand it. Technically, what's happening is we're getting two numbers adding to 0, and then x plus 0 is x. But you can also see it as addition and subtraction reversing or undoing each other. Once again, this is the fourth equation. It is identical algebraically to the third equation, the one right before it. X minus a number equals a number. There's no difference algebraically. We're going to approach this the same way. What do we want to do to each side? Keeping in mind the goal is to get the x by itself. We see that minus 1.9. We want to add 1.9. Plus 1.9. And as soon as I do that to the left side of the equal sign, I have to do the exact same thing to the right side to keep the equation balanced. To keep that seesaw level with the ground. Why did I add 1.9 to each side? Because I saw this. I saw the negative 1.9. That's really what that is there. It's really x plus negative 1.9. There's a minus sign in front of it, so that makes it negative. So those two add to 0. Negative 1.9 plus 1.9 add to 0. Or it may help you to see that addition and subtraction are undoing each other. You start with the x, you subtract 1.9, then you add 1.9, you're back to x, right? These two add to 0. X plus 0, or simply x, equals. And I'd like to think you can add 3.7 and 1.9 mentally. You should be able to do that. Pretty simple. It is 5.6, right? Do it on paper if you need to, but 5.6 is our hypothesis. That's what we think the x has to be in order to make a true statement. So let's prove it. Let's take the 5.6, put it where the x is, and see if we get a true statement. This is where the x was, minus 1.9 equals 3.7. Here's a little thing that happens sometimes when we're solving algebra equations. Sometimes it's harder to check the answer. It's harder to prove that 5.6 is the solution than it is to actually come up with it, right? But if you do 5.6 minus 1.9, you'll have to do a little borrowing or renaming or regrouping, whatever you might want to call it. But 5.6 minus 1.9 is 3.7. So we are now done with our fourth equation. We did two that had addition in them, and we subtracted from each side to solve. Then when we had the two that had subtraction in them, we added to each side to solve. That's what happens. Addition and subtraction reverse each other. 3 times x equals 21. 3 times a number equals 21. And by the way, a third grader, late enough in third grade, or certainly a fourth grader could solve this. The fourth grader or third grader would see it this way, though. 3x box equals 21. This is a times sign here. Here it's a number. This x is standing for a number the way we do it. The fourth grader has the old x meaning a times sign. The fourth grader will, of course, put a 7 in the box. And that's a true statement. 3 times 7 is 21. We're going to say that x equals 7. But it's the same thing as the fourth grader does. All right? Ultimately, we want to say that x equals a number. And we know it's 7. 3 times 7 is 21. But what are we going to do to each side? Well, in the equation is a multiplication. 3x means multiplication. What will reverse or undo multiplication? What do you think? Addition and subtraction undo each other. Multiplication and division undo each other. And I said earlier, our preferred way of writing a division is going to be with a fraction bar. What did I just do there in red? I divided each side by 3. I did the same thing to each side. Why did I divide by 3? Because I'm trying to reverse that multiplication by 3. And the way that this reversal actually happens, I mean, it's legitimate, and it may very well help you to think that I'm reversing a multiplication with a division. If you start with a number x and you multiply it by 3, and then you take that result and divide by 3, you will be back to x, right? That should make sense to you. But this also is mathematically correct. I can cancel the 3's. Even if this were not in the context of an algebra equation. When I teach you 1st and 5th grade about equivalent fractions, all right, we can cancel in this situation. Maybe I'll come back and look at that a little bit more, but we are essentially done because there's the 7. The right side is 21/3 or 21 divided by 3. Either way you look at it, that's 7. And we don't really have to show any work here for the checking because mentally we know 3 times 7 equals 21. Of course, this 3x, the 3 and the x right next to each other means multiplication. If we put a 7 where that x is, we don't get 37. We get, it's 3 times 7, which is 21. So we're done with this one. This idea of canceling, though, is maybe worth looking at a little bit more. Let's say we have 10/15. Now, you know that you can simplify 10/15 down to 2/3. You might think of it as dividing the top and bottom by 5. But 2 times 5 and 3 times 5, right? The 10 can be thought of as 2 times 5. The 15 can be thought of as 3 times 5. And one of the most important truths of middle school math is that in a situation like this, we can cancel those 5's because they're being multiplied. It's the same number, and it's being multiplied 2 times 5 and 3 times 5, and there are 2 5's there, so we can go like this, bang, bang. Now that's equivalent to dividing the top and bottom by 5, but it's this idea of canceling is important to see, and I know that I've taught you that in 5th grade. The canceling here is the same. The only difference is that there's only a 3 in the denominator. I guess you could, if you wanted to, think of this as 3 times 1, and then you would be left with x over 1, but that's x. Those 3's cancel. It's 3 times x, so we can cancel it because it's being multiplied, and this 3 is the same. So it's very similar to the 2 5's being canceled over there. We're now going to do our 6th equation. The 5th equation had a multiplication within it, and so does this one. Algebraically, this is identical to the one that we just did. It's a little more challenging because of the presence of the fraction, but algebraically it's the same. How do we reverse the 2/3 times x? And let me just make this point. Here's a common mistake for people your age first learning algebra. You might look at this and say, I want to subtract 2/3 from each side. But no. In the last equation, we had 3x equals 21. You don't want to subtract 3. You don't isolate the x. If you have 3x and then you subtract 3 from it, that's not x. You can only isolate this x by dividing like this, not subtracting. Subtraction reverses addition. Subtraction and addition reverse each other. Multiplication and division reverse each other. This is multiplication, so we need division. Written as a fraction with canceling. This is done the exact same way as the one right before it. Not subtraction, but division, like this. As soon as I chose to divide the left side by 2/3, I had to divide the right side by 2/3. That is the strategy, the approach of doing the same thing to each side. Those 2/3s can cancel the same way the 3's did before. This is a complex fraction, a fraction that's got fractions in it, but the canceling applies to fractions just like it does to whole numbers. So we can do this. And we have the x isolated by itself on the left side. X equals. Now, it's 12 divided by 2/3. And we did this. This was one of the high water marks, one of the most challenging, advanced things we did in 5th grade was to divide by a fraction. I taught you why we do what we're going to do here. I don't want to do that right now, but I probably will remind you sometime during 6th grade. Why do we flip the second fraction and multiply? We're going to keep the 12 the same, but we're going to flip the 2/3 to a 3/2 and multiply. That's how we divide by a fraction. So this becomes 12 times 3/2. To divide by 2/3, multiply by 3/2. Flip that second or bottom fraction, leave the 12 the same. 12 over 1 is the same as 12, so you don't flip the 12. You flip the 2/3 and you multiply. Now, 12 times 3/2 is 36 halves. Multiply across the top and bottom. 12 times 3 is 36. 1 times 2 is 2. But 36 divided by 2, or 36 halves, simplifies to 18. X equals 18 is the solution. I forgot to say at the beginning, some of you might be able to figure that out mentally. The original equation said, what can you take 2/3 of and get 12? 2/3 of what is 12? And that solution, that unknown number, is 18. If we take 18 and put it where the x is, we get a true statement. I'm running out of room a little bit. Let me come over like this. 2/3 times 18 equals 12. That's the original equation with an 18 substituted for the x. And this is another kind of advanced thing we did in 5th grade. 2/3 times 18 is 12. You need to verify that for yourself. If we have to review multiplications of fractions like that during 6th grade, we will, but in the interest of time, I'll just talk about it quickly. There are 2 ways to do 2/3 of 18. 1/3 of 18 is 6, right? 1/3 of 18, 6. 2/3 is twice as big as that, so it's 12. Or you can multiply across the top and bottom here and get 36 over 3. 36 divided by 3 is 12. So either way you look at it, 2/3 of 18 is 12. We put the 18 where the x was and got a true statement, so the 18 is the solution to our equation. We're going to now look at equations 7 and 8. 2 more and we will be done. At this point, I need to make a disclaimer. I need to say something in the interest of full disclosure and truth. I need to say to you that these final 2 equations I'm going to give you are not as important as the previous 6. The reason is they just don't come up much in the future. As we advance into pre-algebra in 7th grade, a full Algebra 1 high school course in 8th grade perhaps, or 9th grade, depending on the student, you just don't see the equations written this way, this form of the equation. You should still be able to handle them in 6th grade, but I just want you to be aware that you're not going to see them as much as the others in the future. And here's the final time. X over 3 equals 12, or x divided by 3 equals 12. Now, let me make this observation, similar to something I said earlier. Students see a division here. They recognize this as a division because I've taught you that that fraction bar is a division. Students see a division sign, a 12 and a 3. So the first thing that pops into their head is 4. There's nothing wrong with you if that happens. It's perfectly natural. But let me ask you this. Can we put a 4 where the x is and get a true statement? Put a 4 there? 4/3? It's 4/3. It could be thought of as 4 divided by 3, but it's also 4/3. 4/3 is not anywhere near 12. What number can you divide by 3 to get 12? Is what the question is. You could also look at it this way. How many thirds equal 12? Because you can see this as divided by 3, or you can see it as thirds. That's a beautiful thing about this symbolism. Do you see that it's 36? 36 is the number that you can divide by 3 to get 12. Or, how many thirds equal 12? It's 36. X equals 36 here. What do we do to each side? Because whenever we solve an algebra equation, even if we can do it easily mentally, there's always, we can say, I did this to each side, or I could do this to each side to get the x by itself, right? Think of that canceling situation from before. Now the 3 is in the denominator, right? If we could somehow put a 3 in the numerator, we could cancel the 3's and be left with x. Well, how do we get a 3 in the numerator? By multiplying, see? 3/1 is the same as 3. If we multiply each side by 3/1, 3 times x is 3x, 1 times 3 is 3. We don't really need to have that 1 down there. But you multiply, that red 3 there is multiplying the left side by 3. If you're more comfortable with the x there, I mean the 1 in the denominator, that's okay. But I just multiplied the left side by 3, so I have to multiply the right side by 3. Notice I put the 3 in parentheses, 12, then the parentheses with the 3 in it means 12 times 3 is 36. Here's the 36 right here. And why did I multiply each side by 3? Why did that work? Because those 3's cancel. Just like they did before. See, in two equations ago, I think it was, we had 3x equals 21, I think it was, right? The 3x, we put a 3 in the denominator to cancel. Here the 3 was already in the denominator, so we needed a 3 in the numerator, which is a multiplication. That's multiplying that left side by 3. Multiplication and division reverse or undo each other. You were given a division, so you multiply to solve. When you had addition in the equation, you subtracted. When you had subtraction in the equation, you added. The reverse operation. When we had 3 times x equals 21, and then 2/3 times x equals 12, we had multiplication, so we divided to undo that multiplication to get the x by itself, or to be able to cancel. There's really no, we don't have to write out the check of this, because the original equation was x over 3 equals 12. If we put a 36 where that x is, we get a true statement. 36 divided by 3 is 12, or 36/3 equals 12. Either way you want to look at it. One more. Before we finish up this 8th and final algebra equation for this video, I just want to repeat to you, this is not something you're likely to see going forward. It's just the way the algebra in high school algebra is developed. We just don't see these kinds of equations very often. But this says x divided by 1.5 equals 6. It's more challenging than the previous one because of the presence of the decimal number. And it's important to realize that this one is solved exactly like the one before it. Algebraically, they are the same. We had, what did we have before? X over 3 equals 12, and we multiplied each side by 3. Well, here we're going to multiply each side by 1.5. Right? 1.5 I'm going to write it as 1.5 over 1, but it's 1.5. And then over here, times 1.5. I multiplied each side by 1.5. And if these two now came into the same fraction, if we multiply these two fractions, 1.5 times x and 1 times 1.5, we would have that. And the two 1.5s cancel, right? Or, over here I could have done it as well. This 1.5 cancels with that 1.5. We had a 1.5 in the denominator. We needed a 1.5 in the numerator, which means multiplying by 1.5 in order to cancel, okay? And when these 1.5s cancel, you're left with the x all by itself. Can you mentally do 6 times 1.5? 1.5 times 6? You might want to think of it that way. You might want to picture the decimal multiplication mentally, or think of what is 1.5 times 6, because 1.5 is 1.5. And the answer is 9, right? 6 times 1.5 is 9. I said earlier that it is sometimes harder to check the solution, to prove that the solution is the solution, than it is to come up with it. And that's true here. If you put a 9 where the x is, you get this statement, 9 over 1.5, or 9 divided by 1.5 equals 6. Well, now you have to do a decimal division. And remember how we did those? This is a little bit of a challenging one because the second number, or the denominator, is a decimal. So what we learn there is we do times 10 times 10. And we get 90 divided by 15, but 90 divided by 15 is 6. 9 divided by 1.5 is 6. 90 divided by 15 is equivalent to that division, and we can get the 6 that way. You also could have multiplied the top and bottom there by 2 to get 18 divided by 2. That might be easier. 9 times 2 and 1.5 times 2. Right? And then you get 18 over 3, which is 6. But x equals 9 is the solution, because when we put it where the x is, we get a true statement. 8 algebra equations. There were 4 that involved addition in the equation. We subtracted a number from each side to isolate the x. We did 2 of those. Then we had 2 where there was a subtraction in the equation. So we added to each side to isolate the x and get the solution. And with multiplication and division, when we had multiplication within the equation, we divided on each side. Did the same thing to each side because the division reversed or undid the multiplication. Then when we had the division, we multiplied each side by the same number to isolate the x and get our solution. 43 minutes and 30 seconds. We're going to be a little bit short of a typical math class of 45 minutes. And I took this very slowly, step by step. Some of you might have thought I did a little too much. I can understand that. But you hammer home in your minds the theory. And I said some of the things I said repeatedly, doing the same thing to each side. Addition, subtraction, reversing each other. Multiplication, division, reversing each other. The canceling when you have multiplication and division. The addition to 0 when you have addition, subtraction. All those things that I went over and step by step. That's what you need to do when you're learning math. Very soon, any one of these equations that I put up here, you're going to zip it off right away and do a lot less writing than I did. But pay attention to the theory. Pay attention to why we do things. And then it will stick with you, and it will become second nature. It'll be like riding a bike, and once you learn it, you'll learn it for life. Take care, new 6th graders. During this year, starting right now, we're going to be doing algebra. Big kid math. Bye-bye. Have a great school year.